Hello, tech experts. Today we're diving into a hardcore and highly painful topic: context compaction for large language models. We've all used models with so called 200K or even 1 app windows. But anyone who has actually run complex agents in production knows that long windows are by no means a silver bullet. Today, we are going to tear down the industry's most cutting edge context management mechanisms. This is a highly counterintuitive truth. Many developers simply rely on long windows at hardware level, thinking that stuffing all historical records in will get the job done. But the reality is, once you cross a certain token watermark, the model not only makes mistakes, but also incurs extremely high latency and costs. This is exactly why top tier tech giants are quietly shifting to a different strategy. Why do we specifically need context compaction? On the left is the sliding window strategy we used to rely on, which is hard truncation. It's like an amnesiac who forgets their original destination halfway through the journey. On the right, the industry is shifting toward semantic compression. Its goal isn't just to blindly throw away data, but to distill the core facts, instantly multiplying the effective conversation length by 10. Next, let's clarify what context compaction actually is and what specific engineering problems it solves. Let's look at a very specific example. You have an agent help you refactor code, and it's been working for 3 hours. The database table structure you finalized in the first 30 minutes gets brutally cut off in the third hour because the token limit is reached. As a result, the agent suddenly starts fabricating fields out of nowhere. Anyone who has built complex agents definitely understands this frustration. This is the disaster brought about by context rot. Let's visualize this process with a data flow diagram. The user's core intent enters the working memory at the very beginning, but then a massive flood of tool execution logs and error messages pours in. Once it hits the 200K limit, the system is forced to evict the earliest rules, directly causing the final hallucination. What we need to kill is this intermediate step of passive eviction. This is a clear comparison. While hard truncation has almost zero computational overhead, it's fatal for long cycle tasks. Semantic compression requires an extra LLM call to generate a summary, but it can condense the tone constraints and current progress set early on into a system prompt, keeping it within the context. It's like leaving a detailed handover document for your successor instead of just walking away. Let's do a quick pause. The answer is obviously B. Actually, the moment semantic compression is triggered, it doesn't save you money. It might even cost you extra to run a summarization model. Its core value is life-saving, keeping the entire reasoning chain and business rules from collapsing. If we've reached a consensus on this, let's dive into the deep end. Since semantic compression is so important, how do tech giants and mainstream frameworks actually implement it under the hood? Let's break down its three-layer core technical architecture. There are currently three major schools of thought coexisting in the industry. The first is full semantic summarization, which is brute force but effective. The second is like surgery, cutting out only useless, verbose logs while preserving the conversation. The third is UTXCA, which academia and top labs are working on, dynamically adjusting the window based on the model's uncertainty during generation. Let's look at them one by one. When is the best time to trigger compaction? The traditional approach is to set a hard deadline, like 180K, and compress when you hit it, but that's very rigid. Advanced agents today, like LangChain's deep agents, use opportunistic triggers. This means taking advantage of a task's natural boundary, like right after finishing a file or looking up a piece of data, and opportunistically compressing the preceding clutter while the logical loop is closed. This is what true sophistication looks like. To give you engineers the inside scoop, these are the threshold settings of several leading frameworks and models in the industry right now. LangChain is quite conservative, kicking in at 85%. OpenAI's CLI tool dares to push it to 95%. As for Claude 3.7 Sonnet, official best practices recommend intercepting and compacting at around 150K. Memorize these numbers. They'll save you a lot of time when tuning parameters. Let's talk about the cutting-edge UTRKA mechanism. Its underlying logic is stunning. As the model generates tokens word by word, the system monitors its logit margins in real time. If it detects that the model lacks confidence and risks hallucinating, the system immediately triggers a rollback mechanism, expands the context window, retrieves more precise information to stuff in, and then regenerates. This is a highly precise form of dynamic memory management. Now that the theory is out of the way, let's see how top tech companies engineer these concepts into reality. Let's look straight at the code and architecture. Anthropic built a beta feature right into the Claude API. You just pass in a compaction strategy and set a threshold. Once it hits 150K, the API server automatically does the summarization and truncation under the hood. Note an extremely critical parameter here: pause after compaction. It pauses after generating the summary and hands control back to you. Let's look at the core of slide 16 and how Forge Code does it. It looks not only at the token count, but also the conversation turns. The most brilliant part is this reasoning preservation on the right. For models with deep thinking capabilities like Claude 3.7, if you violently compress away its historical thought processes, its subsequent answers will lose logical continuity, like it's blanking out. So Forge code deliberately extracts the recent reasoning process and passes it to the next round of conversation like a baton. This is Forge code's actual configuration file. Do you see preserve, reasoning, true, and reasoning tags below it? When executing compaction, the framework scans the historical messages being evicted, uses regex or parsers to extract the content inside these thought tags, and forcefully appends them to the new context. This is the elegant way senior engineers solve problems. Not all compaction requires firing up an LLM to write an essay. Tools like OpenCode use surgical pruning. What eats up the most tokens when writing code? It's those tens of thousands of lines of error logs and git diffs. OpenCode directly deletes long logs from historical terms, keeping only the latest error. This saves tokens without destroying the conversational semantics at all. Checking everyone's focus. The answer is B. The server pauses after doing the summary for you, so you have the chance to seamlessly splice the most critical recent conversation turns or specific context objects from your system, right after the summary before letting the model continue its response. This gives developers immense control. Seeing this, you might think context compaction is perfect. But as staff level engineers, we have to look at the hidden pitfalls and trade offs when actually deploying this into production. This is the ultimate contradiction faced by all compaction algorithms. Summarization inevitably loses details. For a chit-chat bot, keeping the gist is enough, but for a coding agent, if the argument type of a specific function gets generalized away during compaction, all the subsequent code will throw errors. Therefore, in complex analytical scenarios, pure summarization is dangerous and must be paired with the pruning and reasoning preservation strategies we discussed earlier. Here is an engineering detail that's very easy to trip over. If you throw hundreds of thousands of words of context into the tokenizer to calculate exactly on every single request just to monitor that 180K threshold, your system latency will explode. The way tech giants handle this is by using logarithmic sampling or fast estimation based on character length, only performing an exact calculation when approaching the red line. This is a highly practical performance optimization. Another deep end is the KV cache. The context cache you worked so hard to accumulate instantly invalidates once compaction is executed because the historical content changes, making the next request sluggish. The workaround is to leverage the cache breakpoints feature of LLM APIs. Lock the cache for system prompts and core documents at the very top, so no matter how much you compress down below, the top level cache is permanently effective. There is a famous thesis in academia regarding context management called the bitter lesson. It tells us don't try to manage a model's memory using hyper-complex, rigid, hard-coded rules. Package context compaction as a tool and hand it over to the LLM, letting it autonomously call the tool to clear its own memory when it feels its brain capacity is running low. This is the ultimate future state. Finally, let's look at the future from where we stand today. Which direction is the next generation of context management technology heading? The future direction is crystal clear: hybrid optimization and hardware software co design. On the software side, we'll combine quantization with semantic compression. Unimportant history won't just be summarized, it might even be downgraded directly to 4-bit storage in VRAM. On the hardware side, future AI chips will natively support rapid KV cache swapping and eviction, much like virtual memory in modern operating systems. Let's do a quick review of the three core buzzwords covered today. Semantic compression is our core weapon. UTAK is the ultimate form of dynamic allocation for the future, and the retention window is the crucial preservation parameter you must set in your configs to ensure no cognitive gaps occur in recent conversations. To summarize today's core insight, context compaction is by no means as simple as writing a Python script to slice an array. It is evolving from a passive defense mechanism into an infrastructure level component driven autonomously by agents, complete with reasoning preservation capabilities. This is the evolution from rote memorization to understanding and summarizing. This is the quote I want you to take away. The hardware limit of 200K is just a physical ceiling, but through excellent context management engineering, you can have your agent reliably run ultra long tasks equivalent to 2000K without crashing. That is the beauty of engineering architecture. Actionable advice. Go back and immediately take a look at your company's agent services. If you're still using brainless array slicing for hard truncation, swap it out quickly for a hybrid strategy based on summarization and pruning. Especially for models involving deep thinking, you must extract and preserve their reasoning thoughts. Thank you all for your time, and I'll see you at the next Hardcore Tech Teardown.